Students, in the last session we had learnt about the combination of capacitors in series. We had derived an expression for equivalent or effective capacitance of two capacitors when connected in series. You know that devices are said to be connected in series if they are connected end to end. In the diagram you can observe the end of first capacitor is one end of the first capacitor is connected to the one end of the second capacitor. So such a combination is what is called as series combination. Whenever devices are connected in series, the charge or current across each device would remain to be the same. Here you can observe the charge on each plate of the capacitor is same, Q. And also the potential applied across the combination of the devices in series divides across each device. So V is the applied potential difference across the combination, which divides into V1 across the first capacitor C1 and as V2 into across the second capacitor C2, such that V will be equal to V1 plus V2. So we had learnt about this combination of capacitors in series. We had derived the expression as the effective capacitance is given by 1 by Cs is 1 by C1 plus 1 by C2, where C1 and C2 are the capacitances of the two capacitors in the combination. Cs is the effective capacitance. So if you have n such capacitors in series, then 1 by Cs is 1 by C1 plus 1 by C2 plus 1 by C3 plus etc. 1 by Cn. So we can say that the reciprocal of the effective capacitance of a combination of capacitors in series is equal to sum of reciprocals of individual capacitances. We had observed few things. So in series combination, the reciprocal of the effective capacitance is equal to the sum of reciprocals of capacitances of individual capacitors. In series combination of capacitors, the effective capacitance is always lower than the lowest of the individual capacitances. This also you have to remember very well. Also, you can recall that this series arrangement is always preferred whenever the required capacitance is lower than the available capacitances. So if you increase the number of capacitors in series combination, then that results in decrease of the effective capacitance. This is one more very important point. If there are n identical capacitors connected in series combination, then the effective capacitance is given by C by n, where C is the capacitance of each individual capacitor and n is the number of such capacitors connected in the combination. Okay. Today we will continue our discussion with the combination of capacitors. We will start our discussion with combination of capacitors in parallel. See, devices are said to be connected in parallel if they are connected between two common points. For example, here you can observe the two capacitors C1 and C2 have their endpoints between two common points. I can call these common points as A and B. See, if I call this point as A and this point as B, you can observe the endpoints of C1 is at A and B and the endpoints of C2 is also at A and B. So the devices are said to be connected in parallel if they are connected between two common points. You may have any number of such capacitors. If all the available capacitors are connected between two common points, then such a combination is said to be parallel combination. Whenever devices are connected in parallel, the charge of the combination divides across the available devices. So if you say Q is the charge of the combination, you can find charge Q1 on C1 and Q2 on C2 such that Q1 plus Q2 would be equal to Q, where Q is the total charge of the combination. Whereas the potential across each device would remain same when connected in parallel. If V is the applied potential difference across the combination, the same potential difference is observed across C1 and also C2. So remember, whenever devices are connected in parallel, the charge of the combination divides across the devices connected in parallel, whereas the potential difference across each device would be the same and would be the same as that across the total combination. So now we have to think about deriving an expression for effective capacitance. So here the charge divides, as I have already told you. We will consider this as the first expression. Q is Q1 plus Q2, where Q is the charge of the combination, Q is the charge across the plates of the first capacitor, and Q2 is the charge across the plates of the second capacitor. Also, from the definition of capacitance, we know that Q1 is C1 into V. V is the potential difference applied across the combination, which would be the same also across C1 and C2. So Q1 would be C1 into V and Q2 would be C2 into V. So Q is C1 into V plus C2 into V, or Q is V into C1 plus C2. Now at this stage I will replace the combination of capacitors by an equivalent capacitor. So the combination of these two capacitors is been replaced by a single capacitor, what is called as an equivalent capacitor. An equivalent capacitor of a combination of capacitors is that single capacitor which produces the same effect as produced by the combination, or which produces the same capacitance as produced by the combination of capacitors. So the equivalent capacitance is said to be Cp. So V is the potential difference across the plates of this equivalent capacitor. Q is the charge on either of the plates of the capacitor. So I can write here that Q is also equal to Cp into V, just like how we wrote these two expressions. So comparing equations 2 and 3, LHS is same. You can equate RHS. Cp into V is equal to V into C1 plus C2. So V gets cancelled on either side. Cp is C1 plus C2. So this is the expression for effective capacitance or equivalent capacitance of a combination of two capacitors connected in parallel. If you have n capacitors connected in parallel, then Cp, effective capacitance, would be equal to C1 plus C2 plus C3 etc. plus Cn. That means the effective capacitance of a combination of capacitors in parallel is equal to sum of the individual capacitances. See, that's what the definition says. Effective capacitance in parallel, the effective capacitance of a number of capacitors connected in parallel is equal to sum of the individual capacitances. In parallel combination, equivalent capacitance is the sum of the individual capacitances. The effective capacitance will be always greater than the greatest of the individual capacitances. That means, let us suppose I have 3 capacitors of capacitances, 1 farad, 2 farad, 3 farad. So highest is 3 farad. Now if I connect them in parallel, the effective capacitance will be 1 plus 2 plus 3, which is 6, which is greater than the greatest of the capacitances 3. So the effective capacitance is always greater than the greatest of the individual capacitances when connected in parallel. So when do we depend on this arrangement? This arrangement is used to get higher capacitances from the capacitors of smaller capacitances. So whenever you are building a circuit, if the required capacitance is greater than the capacitance of the available capacitors, then you have to depend on parallel combination. If you increase the number of capacitors in parallel combination, that results in increase of the effective capacitance of the combination. Also, if n identical capacitors of each of capacitance C are connected in parallel, then the effective capacitance in parallel Cp would be given by n into C, where n is the number of capacitors in the combination, C is the capacitance of each capacitor. If you remember, in series, for n identical capacitors connected in series, Cs was given by C by n, but here it is n into C or C into n. Okay, so this is about the combination of capacitors. We have discussed about a series combination of capacitors and parallel combination of capacitors. Next topic that we have to discuss about is energy stored in a charged capacitor. In fact, we will be deriving an expression for the energy stored in a charged capacitor. You know that when a capacitor is charged, the charges will be stored on the plates of the capacitor. So the stored energy is also called as potential energy. So here we will be deriving an expression for potential energy of a charged capacitor. In order to understand this situation, I will consider a capacitor here. Let me say I have a capacitor which is connected to a battery like this. See, when the battery is switched on, charges gets stored transferred onto the plates of the capacitor. When the capacitor gets completely charged, in fact the capacitance of the capacitor is C. When the capacitor gets completely charged, the final charge on each plate of the capacitor will be capital Q, plus Q on one plate and minus Q on the other plate, and the potential difference across the plates of the capacitor would be V volt when it gets completely charged. So now I explain the situation once again. We have considered a capacitor of capacitance C. Initially it is an uncharged capacitor. Now it is connected to a external power supply. When you switch on the battery, charges gets transferred onto the plates of the capacitor. So charges slowly gets accumulated onto the plates of the capacitor. Remember, it is not an instantaneous process. When the capacitor gets completely charged, the total charge would be capital Q on each plate, and V would be the potential difference across the fully charged plates of the capacitor. So here we have considered a capacitor which is initially uncharged. When battery is connected across the capacitor, the charge transferred from one plate to another plate bit by bit in small amounts of dq from 0 to q. Initially the total charge on the plates was 0. Now when you switch on the battery, slowly the charges gets transferred onto the plates bit by bit. It has been said that at each instant a charge of dq is been transferred, and finally the charge on the plates would be q. Now during the process of charging of the plates of the capacitor, we will consider an intermediate situation when the charge on the plates are plus q and minus q. That means it has not yet got completely charged. Still the process of charging is continued, Now at this stage the charge on each plate is small q. Now we shall think of transferring a small charge dq onto the plates of the capacitor. So when the charges are plus q and minus q, the potential difference across the plates is v dash. When it gets completely charged, it would be v. Now it is still partially charged. So now the potential difference between across the plates of the capacitor is v dash. You know that v dash is given by q by c. That's by the definition of the capacitance. Now, if you think of a transfer of charge of dq onto the plates, you know that the work done in transferring a charge of dq would be v dash into dq, because you know that v is w by q or w is v into q. That has been made use here. The work done in transferring a charge of dq onto the plates of capacitor is v dash into dq. So substituting equation 1 into dw would be v dash is q by c into dq. So see, this is the work done in transferring a charge of dq onto the plates of the capacitor. But now we want to know what is the total work done in transferring a charge of capital Q onto the plates of the capacitor, because this total work done will be stored as potential energy. So total work done is given by integrating this dW between 0 to capital Q. So work done is given by integral of dW is q by c into dq from 0 to capital Q, or W is, c is an constant. It is the capacitance of the capacitor. So you can take it out of the integral sign. You will be left over with W is integral from 0 to q into dq. So q into dq is, you know that the integral of q would be q square by 2. You know that integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. Here also q to the power of 1 plus 1 divided by 1 plus 1. So it will be q square by 2. If you remember, see, we had learned that integral of x to the power of n is x to the power of n plus 1 divided by n plus 1. Now in this situation, what is n? N is equal to 1. So 1 plus 1 will be 2 divided by 1 plus 1 will be 2 between 0 to q. So W will be equal to 1 by c. Applying the limits, applying the limits, in place of small q will apply the upper limit q square by 2 minus 0 by 2. 0 is the lower limit. So W is q square by 2 into c. So the work done in transferring a charge of capital Q onto the plates of the capacitor is given by q square by 2c. This work done is stored as potential energy. So potential energy stored in capacitor is given by U is q square by 2c. So also you can write it as half CV square and half into q into v. That is because you know that U is q square by 2c. You know that q is c into v. So U would be c square v square by 2c. What happens? 1c gets cancelled. So half cv square. That's what is been written here in one expression. See, half cv square. Also it will be q into v, because you know that q square by c. You know that v is c is q by capacitance is charged by potential. C is Q by V or V is Q by C. So you can also write it as half into Q into V. That's what is being written here. The last topic of this chapter is about lightning conductors. Students, you might have observed this. If you have seen tall buildings, on the top of tall buildings you can find some metal structures which will have spikes on them. Spikes means a metal piece having a sharp edge. So a lightning, see like this, you have a tall building on which you have these spikes, metal conductors with sharp edge. The other end of the metal conductor will be connected to earth through copper wires. So a lightning conductor is a device which is used to save big buildings, big means tall buildings, from the lightning strokes. See, you know that there will be discharge of electricity due to the friction amongst the clouds towards the environment of the earth, and these charges created will reach the earth through some medium. So when you have tall buildings, always there is a danger of these charges flowing through the building to the earth. So in order to avoid the charges flowing to the earth through the building, you will have these spikes connected to the top of the top buildings. So you know that sharp edges always attracts charges. Charges accumulated sharp edges of a conductor. So the charges would get attracted towards the sharp edges of this conductor, and then they will flow to earth through this conductor. So a lightning conductor is a device which is used to save tall buildings from the lightning strokes. A lightning conductor is a flat, thick strip of copper with several sharp spikes, that is pointed conductors, projecting above the highest part of the building. If a lightning stroke does strike the lightning conductor, the electric discharge passes down the copper strip to the earth. So this prevents the high current from passing through the building, thus ensuring the safety of the building and also the occupants. So you can observe these lightning conductors in tall buildings. You will not find them normally in buildings having 1 or 2 stories, because that is not necessary, but only in very tall buildings where you have multi-stories, you need these lightning conductors, because there is always a danger of the charges which are being released to the earth's atmosphere from the clouds flowing to the earth through these buildings. So to avoid that, these lightning conductors are being always erected on the top of buildings. Thank you, students. We will recall whatever we have discussed in this chapter in the next session, and then we will continue with numericals. If you want any clarification, if you have any doubt, you can WhatsApp me. Thank you.